Hello, this is part 2 of Lecture 6b for ECE 361, Probability for Engineers, Fall 2016. In this second part of the lecture, we're going to cover Section 3.4, Joint PDFs of Multiple Random Variables. And this will have 4 subsections. We'll talk about joint probability density functions, joint cumulative distribution functions, expectations of multiple random variables, and how to extend everything to more than 2 random variables. Let's first talk about joint probability density functions. Recall that from when we first introduced the notion of a continuous random variable and its probability density function, little f sub x, for a random variable x, we said that the defining property of that PDF is that it satisfies the equation here, which says that for any subset B of the real line, the probability that x is in that subset should be computable from integrating the PDF over all little x in that set. That must be true for any B. Any function f sub x will correspond to a valid probability density function, provided it has 2 key properties. One is that it is non-negative, and the second is that it is normalized, where normalized means if I integrate it over all possible values of x, namely from negative infinity to positive infinity, I will get unity. Finally, recall that when we introduced PDFs, we said that PDFs are not probabilities, rather they are probability densities. And in particular, I'd like you to think of the PDF little f sub x at some value little x to be interpreted as the probability per unit length for that distribution at that value. And the motivation for that interpretation was the following argument. Let's consider a particular choice of B here, namely B is the small interval of width delta. We think of delta as some small positive number. The small interval of width delta at x, that is looking at the interval from x to x plus delta. So using this definition up here, the probability that the random variable x is in that interval x to x plus delta is the integral from x to x plus delta of the PDF over all t in that interval. Now, if you recall from calculus, we interpret the integral as a sum where we first segment the real line into increasingly small size subintervals, and we evaluate the sum, or the integral, as the sum of the heights of the rectangles that fit under the curve with widths equal to delta. So in this case, when I'm only integrating over a small interval x to x plus delta, I'm really only adding one such rectangle, and so we have the natural approximation of this integral is the height of the rectangle at x times the width of the rectangle delta, and so therefore I can then solve this approximate equality. The probability that x is in this interval is approximately equal to the density at x times delta for the density, and I get this expression here, which says that the probability density function for the random variable x at the value little x is the ratio of the probability that the random variable x is in that interval of width delta divided by the interval width. So this is probability per unit length. So keep that in mind, these 3 things, that the PDF for a single continuous random variable is interpreted as having the property that if I integrate that function over any region B, I get the probability that the random variable x is in that set, that the PDF must be normalized, means if I integrate over all possible values I get 1, and that I can interpret the PDF as a probability density per unit length based on an argument like this, which corresponds to a Riemann sum argument from calculus. All right, so none of this should be too surprising, given that we've done this exact same extension for joint PMFs of multiple discrete random variables in the previous chapter. All we're doing now is making the logical extensions from discrete to continuous and from single continuous to multiple continuous random variables. Everything is rather coherent. So what we're going to consider now is a pair of continuous random variables, x and y, and we say that they are jointly continuous if there exists a function, which we call the joint PDF, that has this property here. And we'll go over the property in a minute, but first let's look at the notation. First, consistent with the case for a single random variable, we use the little case f to indicate a PDF. The subscripts having capital letters indicate the random variables corresponding to that PDF. In this case, this is the PDF for the pair of random variables, capital X, capital Y, and we are evaluating that PDF for that pair of random variables at these two arguments, little x, little y. Now, in perfect analogy with what was on the previous slide, we now say that this PDF, f sub xy, has the property that the probability that the pair of random variables, x comma y, is in this region B, where now B is a subset on the plane, the xy plane. The probability that that pair of random variables lies in that region B is found by integrating, and this is a double integral, integrating over all xy pairs in that set, the density at each point x comma y. So now if I take the special case when B is the entire plane, then of course we're going to have the normalization requirement being, in this case, the double integral from negative infinity to positive infinity for both x and y of the PDF must evaluate to 1. And finally, to extend this notion of PDF as probability per unit length, the corresponding notion now is probability per unit area. So now, if you recall your calculus on 2D functions, we can have a function with arguments x and y, and if we think of that function f of xy as the value of the function at the point xy on the plane, then we can integrate that function over a region by first chopping up the xy plane into very small squares with side length delta, and we approximate the integral by summing over all squares in the region the area of, or the volume of the rectangular cube. Namely, it has a base area of delta squared on the xy plane, and then the height of that cube is f at xy. So the same argument can be done here. So now we're going to consider some point a comma c in the xy plane and some small value of delta, and we're going to consider a particular value of b, like here. This is the generic case. Now we're considering a particular case of b, and this is the small square we're considering. It's the square where the first, considering of all points, where x is between a and a plus delta, and y is between c and c plus delta. So this is the square with lower left-hand corner point a comma c and side lengths delta and delta respectively. And thus, of course, the area of that square is delta squared. Then the probability that xy is in that particular choice of b listed here is going to be found by integrating over all y from c to c plus delta, over all x from a to a plus delta, the joint PDF at each point in that square. And again, using that Riemann integral approximation I just mentioned, that integral is going to be approximately given by the height of the function over that square, which is approximately fxy at AC, times the base area delta squared. So again, if then I divide both sides of this equality by delta squared, I can see that the PDF, little f sub xy at AC, is roughly the probability per unit area at the point. Well, in this case, AC, not xy. So all the notions on the previous slide that were defined for a single random variable extend in the natural way to two random variables. All right, so let's recall this notion of obtaining the marginal distribution from the joint distribution. We discussed this in the context of multiple discrete random variables. So let's let the pair u comma v be a pair of discrete random variables, and suppose they have some joint support a on the xy plane, and they have a joint probability mass function, little p sub capital U comma v, which is shorthand for the probability that the random variable u takes value little u, and the random variable v takes value little v. And this PMF has the defining property that if I sum up that joint probability mass function over all pairs uv in the support script A that I will get 1. That's the normalization requirement for a joint probability mass function. We also showed that it's possible to obtain the marginal probability mass functions, that is, the probability mass function for u by itself and or the probability mass function for v by itself from the joint PMF by simply summing over the other variable. So in particular, the probability mass function for the random variable u, where little u is a fixed given element in the support, is found by summing over all possible values of v. And what am I summing? I'm evaluating the probability mass function, the joint probability mass function, where u here is fixed by the argument on the marginal, and v is the dummy variable of summation. And likewise, a similar thing holds true for obtaining the marginal for v. Instead, now I'm going to sum over all possible values of u. So keep this in mind because the analogous concepts are going to apply for the case of joint probability density functions. Okay, so let's go back to the continuous case. Now we think of the pair x and y as jointly continuous random variables with a joint PDF, little f sub capital X, capital Y, at some point, little x, little y. And we think of A as a subset of the real line, okay? So we think of A as some interval of interest, say, for the random variable x. And so if I wanted to know the probability that the random variable x was in A, and all I had access to was the joint PDF, then the event that x is in A is equivalent to the event that x is in A and y is in the reals. Why is that fine? Because y is always in the reals, so adding this requirement does not affect the probability that x is in A. But what it does make clear is that I'm asking for an integral over all pairs xy where x is in A and y takes any value. That's why I'm integrating here over all x in A and over all y from negative infinity to positive infinity. And what am I integrating? Of course, I'm integrating the joint PDF. So now, if I take the case where I want x so that A is equal to some particular point, little x, it can be shown that I'm going to obtain the marginal PDF for the random variable x at little x. We're not going to prove that, but it's easy to see that if you understand the argument probability per unit length given before. So in particular, given the joint PDF, little f sub x comma y, I can obtain the marginal PDF, that is the PDF for just the random variable x alone, by integrating the joint PDF over all possible values of y. And by symmetry, I can obtain the marginal PDF for the random variable y by integrating the joint PDF over all possible values of x. Okay, so now we're going to do a rather famous example that dates back several hundred years. And there was a French mathematician, the Comte de Buffon, who asked the following question. Suppose I have a floor where the floorboards are lined and the distance separating each floorboard is the parameter d. And now I take a needle and I drop the needle of length L onto the floor. And I want to understand the probability that such a needle will hit the line beyond one of the lines separating two of the floorboards. And so there's two key parameters here, namely L, the length of the needle, and D, the distance separating the floorboards. And although an extension for the case L greater than or equal to D is possible, for now we'll do the simple case where L is less than D. And that's simpler because if L is less than D, you should be able to see that no needle can ever intersect two lines. Okay, so either the needle does not intersect any lines, as with this needle here, or this one here, or it intersects one of the lines here, 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 or here. Okay, and this figure comes from the URL given below. And let's then try and answer this question using probability, in particular, this notion of joint PDFs of multiple random variables. Okay, so we're going to define some notation. First, we're sticking with D as the distance separating two vertical lines on the floor. And now we're going to, again, retain the fact that our needle has a length L. And we're going to look at the center point of our needle. And so, of course, if I look at the center of the needle, then the distance from here to here is L over 2, and the distance from here to here is L over 2. And I've added an arrow to the needle for no essential reason. Now, I'm defining two key variables. So I'm going to drop this needle uniformly at random. And what that means is that it can end up in any position whatsoever with equal probability. Okay? To make that more precise, we're going to understand what does it mean to characterize the position of the needle. Well, we're going to do that with a pair of variables. They will eventually become random variables, x and theta. So x is defined as the distance from the center of the needle to the nearest floor line. And a little thought shows you that that distance cannot be less than d over 2. Because by definition, we're always going to the nearest floor line. So there's a distance of d, and so wherever you end up, there's a distance that's less than d over 2 between the center of the needle and the nearest floor line. Okay, so in this case, this one's the nearest floor line. Now, the other parameter is theta, and that's the angle made by the orientation of the needle relative to the horizontal line. Okay, so that's what theta is. And the key observation then is that the length of this, I can look at this triangle here, and I see that this hypotenuse has length L over 2. And if this hypotenuse has length L over 2, and this angle is theta, then this quantity right here is L over 2 times sine of theta. Okay, so this quantity right over here is, in words, it's the distance on the x-axis between the center of the needle and the end point of the needle closest to the next floorboard. Okay, that's what L over 2 sine theta is. Okay, so we're going to keep that in mind because we're going to compare x, the distance from the center point of the needle to the nearest floor line, with L over 2 sine theta, the distance from the center of the needle along the x-axis to the end point of the needle. All right, so it should be clear then that x is the distance from the center of the needle to the nearest line, less than or equal to d over 2. Theta, the acute angle made by the needle relative to the horizontal, is going to be theta in the interval 0 to pi over 2, 90 degrees. And so if the needle is truly random, then its distance from the nearest line is uniform over the support 0 to d over 2, and the angle it makes is also uniform over its support 0 to pi over 2. And furthermore, the distance x and the angle theta are themselves independent. And so it follows that the joint probability density function of the pair capital X capital theta is the product of the joint PDFs. We'll talk about this more when we talk about independence later this lecture or next lecture. But when you have independent random variables, recall that in the discrete case, when we had independent discrete random variables, their joint probability mass function was the product of their marginal probability mass functions. The same thing holds true in the continuous case. When I have a pair of continuous random variables with joint PDF, if they're independent, then their joint PDF is equal to the product of their marginal PDFs. Now, in this case, we know the marginal PDFs. In particular, we know that the distance, the random variable x, is uniform from 0 to d over 2, and therefore the probability of any value x in that support is 2 over d. Recall that the uniform distribution must integrate to 1, so that's required. And likewise, the PDF for theta is uniform over 0 to pi over 2, and therefore the probability of any value theta in that support is 2 over pi. And so multiplying those two PDFs together gives you the joint PDF 4 over pi d. Okay? And that's the joint PDF for any x, this is a typo, x and theta, where x is in 0 to d over 2 and theta is in 0 to pi over 2. Okay, so again, recall our picture, and now observe that the event that the needle hits the line is equivalent to saying that the distance from the center of the needle to the nearest line, x, is less than the distance on the x-axis from the center of the needle to the tip of the needle, which is L over 2 sine theta. So I've translated, using these concepts, the English statement that the needle hits the line into the mathematical equation that the random variable x must be less than or equal to L over 2 sine theta. So the probability of hitting is the probability that the pair x and theta obey this relationship. And so now what I'm going to do is to evaluate this probability, I'm going to integrate over all possible x theta pairs that satisfy that relationship. So this means integrate over all x theta in the support of x and theta that further obey the requirement that x is less than or equal to L over 2 sine theta. And now what I do is I substitute in the value of the joint PDF, which we computed on the previous slide. Remember that was 4 over pi d. And now I have the double integral where x is going from 0 to L over 2 sine theta, and theta is going from 0 to pi over 2. And I'll skip the details of the integral. You should work on it your own. And what you'll find at the end is that that probability of hitting is given by a rather simple expression. Namely, it's the quantity 2L over pi d. So remember that L and D were the original parameters, L being the length of the needle and D being the floorboard separation distance. Now, one of the original thoughts here was that when this was derived, it was observed that the quantity pi pops in, and it may or may not be intuitive to you as to why pi should appear, but nonetheless it does. And so if you were to solve this, if we let p, little p, be the probability that the needle hits, we just showed on the previous slide that little p equals 2L over pi d. And I could solve this equation for pi, and I would have 2L over pd. And the reason for doing that, one possible reason, would be that I can estimate what p is. How? By simply dropping a lot of needles and looking at the fraction that hit the floor. That's what this bullet here says. We can estimate the parameter p, the probability of hitting, by dropping some large number n of needles and forming the estimate p hat of n, where this says, give me the number of needles that hit the lines divided by n. So this is, in other words, the fraction of the n needles that hit the line. And it should be intuitive to you that if I drop a large enough number of needles n, that'll be the probability, or close to the probability, of any given needle hitting the line, p. So if I was able to do that and get a reliable estimate for p, then I could substitute my known values for L and D and my estimate for p to get an estimate for pi, the numerical constant. So in particular, my estimate for pi using n needles is the ratio 2L over p hat n of d. And so I wrote this up in a few lines in Mathematica. I think I give them on the next slide. And this is the estimate of pi. And it's hard to see, but there's a horizontal grid line right at pi here, running along here. And this is for n going from 1 up to 1,000. And what I've done is I've tracked the running estimate of pi as n increases. And you can see that after only even maybe 100 needles, it stabilizes, and there's some fairly accurate estimates as to what pi is. And here's the Mathematica code, in case you're interested, used to create the plot on the previous slide. Okay, let's move on to joint cumulative distribution functions. Okay, so let's recall from the case of a single continuous random variable with the probability density function little f that I can always obtain the CDF from that little f by integrating the PDF over all t between negative infinity and x, where x is the argument of the CDF, the value of interest. And again, this is in perfect analogy with the analogous quantity in the discrete case. If I had a discrete random variable y with the probability mass function little p sub y, then its CDF, capital F sub y, is found by summing up the PMF, p sub y, at all values x less than or equal to y. And the basic underlying analogy is this is the probability that the random variable y is less than or equal to y, and the event that the random variable y is less than or equal to little y is the union of the disjoint events that the random variable y equals the value x over all possible values of x that are less than or equal to y. So to be more concrete, the event that y is less than or equal to 4, if y takes values 0, 1, 2, 3, 4, 5, 6, is the sum of the event that y equals 0, or y equals 1, or y equals 2, or y equals 3, or y equals 4. And we then saw, when we talked about multiple discrete random variables with a joint probability mass function, that their joint cumulative distribution function, capital F sub xy, which stands for the probability that the random variable x is less than little x and the random variable y is less than little y, is found by summing over the joint probability mass function over all pairs uv that satisfy the requirement that u is less than or equal to x and v is less than or equal to y. It is precisely this set of uv pairs that correspond to the events that x is less than little x and y is less than little y. Finally, we also saw in the case for a single random variable, in the continuous case, that the probability density function, little f sub x, is obtainable from the cumulative distribution function, capital F sub x, by differentiating it. So keep all these things in mind as we now talk about joint cumulative distribution functions of multiple continuous random variables. Okay, so no surprises here. The joint cumulative distribution function of two continuous random variables, x comma y, is the CDF capital F sub xy, and it stands for the probability that the random variable x takes a value less than or equal to little x, and the random variable y takes a value less than or equal to little y. And again, I can obtain this joint CDF by integrating the joint PDF. In particular, if I want to evaluate the joint CDF at some candidate values, little x, little y, then I integrate over all possible values for s and t, where s goes up to x and t goes up to y. And again, if I happen to be given the joint CDF and I wanted to instead obtain the joint PDF, then I can obtain it by simply differentiating, except now I have to differentiate twice. I first take the partial derivative of the joint CDF with respect to x, and then take the partial derivative with respect to y. Let's do an example. Let's suppose that the x and y are a pair of jointly continuous random variables with a joint cumulative distribution function, capital F sub capital X capital Y, given by this expression here. And the question is, find the joint probability density function. Well, what we just saw at the bottom of the last slide was, to do so, we do a double differentiation. First, we differentiate with respect to x, then differentiate with respect to y. So I've indicated that here. I'm going to differentiate with respect to x, then I'm going to differentiate with respect to y, capital F. And so I substitute in the particular form that's assumed for the capital F, and I recognize that all the x's are separate from all the y's, and so I can factor this. So this is really the product of the derivative with respect to x times the derivative with respect to y. And if you differentiate these functions, you of course get these expressions here, lambda e to the minus lambda x times mu e to the minus mu y. Now, once you're more comfortable with this material, and just looking at this, you will see, oh, this is the joint CDF that corresponds to the product of two exponentially distributed random variables that are independent of one another. That is to say that we know that x, from this definition, we know that x is exponentially distributed with parameter lambda, y is exponentially distributed with parameter mu, and x and y are independent. And so it follows then immediately, without having to do this calculation, that their joint PDF will be the product of their marginal PDFs, and these are the known marginal PDFs for x and y. But this definition applies in general, not just for that case. Okay, next let's talk about expectation corresponding to functions of multiple continuous random variables. And you'll recall that when we talked about single continuous random variables x with a PDF little f sub x, and we considered some other random variable y obtained by evaluating x at some function g, then I can find the expected value of y, that is the expected value of g of the random variable x, by integrating over all possibilities of x, and then for each such x, evaluating the function g of x and weighting it by the probability density f sub x at little x. So in perfect analogy with that definition, let's now let the pair xy be a pair of jointly continuous random variables with joint probability density function little f xy, and let z be some arbitrary function g of the pair of random variables xy. Then if I want to know the expected value of z, I'm going to do the natural thing. I'm going to integrate over all possible values of y, integrate over all possible values of x. For each possible pair xy, I evaluate g at that pair, and I weight it by the probability density function at that point. Let's do an example. Let's suppose that x is an exponential random variable with parameter 1, and y is an exponential random variable with parameter 1, and they are independent of one another. And let's let z equal to the harmonic mean of x and y, that is the square root of their product. And we want to find the expected value of z. Okay, so this is a particular function g of x and y that I've chosen. So now I want to know the expected value of z. I evaluate over all possible values of y going from 0 to infinity, all possible values of x going from 0 to infinity. This is gxy, and this is the joint PDF of x and y. It's simply the product of two exponentials. Now in this case, these integrals can be factored. So this is the integral from 0 to infinity of root x e to the minus x, and the same thing here. Integral from 0 to infinity of root y e to the minus y. And that integral can be evaluated, although it requires the error function. And you can show that each such integral equals root pi over 2, and so their product is pi over 4. And therefore the expected value of the harmonic mean of two unit rate exponential random variables is pi over 4. And you'll recall we've talked many times by this point about linearity of expectation. It continues to hold in the case of multiple continuous random variables. So in particular, if x and y are jointly continuous, then they have means ex and ey, then the expected value of the linear combination ax plus by is the linear combination evaluated at the means. And finally, let's talk about more than two random variables. We did the same thing when we introduced discrete random variables. We first talked about what happens when you have a pair of discrete random variables, and then we talked about what happens when you have more than two discrete random variables. So now we're doing the same thing with more than two continuous random variables. Suppose we have three, and we'll call them x, y, and z. We say that x, y, and z are jointly continuous with probability density function f sub x, y, and z if they have the following property, that if I choose any b, which is a subset of R cubed, the domain in which x, y, and z live, then the probability that that triple of random variables takes a point anywhere in that subset B can be evaluated using the joint PDF by integrating that joint PDF over all possible tuples x, y, and z in that set. And I can marginalize the random variable z by integrating over it. So if I start with the joint PDF little f's of x, y, and z, and what I want is the joint PDF for x and y without reference to z at all, I simply marginalize out, that is, I integrate over all possible values of z from negative infinity to positive infinity. And now suppose I further wanted to marginalize out and just have the marginal distribution for x. Well, I'm going to take that joint distribution fxyz and integrate over all possible values for y and z, that is for the two variables whose values I don't care about. The natural thing. And of course, if I had a triple of continuous random variables x, y, and z, and I had some function g, that if I evaluate g at x, y, z, I get a random variable w, and I want to know its expected value, naturally what am I going to do? I'm going to consider all possible values that x, y, and z might take. I'm going to compute the value g at that tuple. I'm going to evaluate the probability density function at that tuple and compute the integral. Finally, expectation of the linear combination ax plus by plus cz equals that linear combination evaluated at the means. And of course, more generally, if I had random variables x1 through xn and numbers a1 through an, and I consider the linear combination, expected value of the linear combination a1x1 all the way summed up over all the way up to an xn, in other words, expectation of this sum, then the expectation of that sum is the sum of the expectations appropriately weighted by the AIs, as you would expect.